Welcome to class number 18 of transport phenomena in mesoscopic and nanoscopic systems. So last day we saw that when the Green's function is given, of course the Green's function in energy domain is given by this form, where eta is an infinitesimally small number multiplied by this identity matrix I. In that case, the Green's functions, the different Green's functions in time domain basically satisfy the equation. So this is a matrix. Okay, now although we have shown this equation or the Fourier transformation of this GE to be this GT, where GT basically satisfy this entire equation, although we have shown these equations, all these equations in the eigenspace basis of the Hamiltonian, remember that a equation or a relation between operators. So an equation for with operators is basically a relation between different operators. Okay, an equation defines the relations between different operators. Okay, so remember that a relation between operators, for example, this GE basically relates this Hamiltonian operator and this operator, and then this is also kind of can be stated as an operator because it is a matrix. So this all relates these operators, and then this Green's function again defines or relates these operators, relates to this all these operators. So we have shown earlier that a relation between operators which is valid in one basis space should be valid in other basis spaces as well. Okay, so it really doesn't matter that in which basis set we define the Hamiltonian or in which basis set we define this Green's function as a function of energy. This relation or this relation is going to be valid in any basis set. Okay, however we define the Hamiltonian, or in irrespective of the basis set in which we define the Hamiltonian, or irrespective of the basis set in which we are working, these relations are always valid. Okay, so we have basically shown these two equations earlier, but now remember that a channel which is not isolated but which is coupled to the contact, the Green's function for that channel, so this is basically given by an equation of the form GE equals to EI minus H minus sigma inverse. Okay, so here H and sigma are matrices, and sigma we have shown that sigma basically depends on the contact Green's function and the coupling between the channel and the contact. So these two equations are basically for isolated channel or isolated contact case. And this equation is for the channel which is coupled to the contact. Now the Green's function in this case is given by this form over here. Now it is actually important to understand the essence of this matrix sigma, that what this matrix actually does to the wave function, or what is the physical significance of this matrix sigma. Although we have stated that this matrix takes into account boundary conditions, and what this matrix denote is that the channel is coupled to the contact, so the channel wave function spill over the contact and excites and creates additional perturbation in the contact, and those perturbation again return back to the channel. So this matrix sigma basically denotes that how this perturbation inside the channel is coming back to the channel itself, or how the wave function excitation inside the channel is coming back to the channel itself via an excitation in the contact. Okay, so this kind of takes into account the boundary conditions of the channel. Now we can actually again get the inverse Fourier transform of this matrix GE over here. Okay, and let us simplify things and assume that the channel consists of only one basis function. It can be one point if it's a spatial basis, or it can be one component of the momentum eigenbasis, or it can be one component of the energy eigenbasis. But right now let us say that the channel consists of only one basis function. Okay, there is only one basis function that defines the channel. Okay, so if there is only one basis function that defines the channel, then all this Hamiltonian H and this matrix sigma, this basically become numbers, because there is only one basis function. So there is no matrix here, these all become numbers. So assume that the channel can be defined by only one basis function, and let this basis be an element of the energy eigenfunctions. So in that case the Hamiltonian reduces to a simple number epsilon, and sigma again reduces to a simple number. Let us call that number also sigma. So this matrix then becomes a number. So GE is in that case given by 1 by E minus epsilon minus sigma. So epsilon is a number which defines the energy level inside the contact, or the valid energy level inside the contact, and sigma is also a number because only one basis function is defining the channel. Okay, and E is basically the variable for energy. Now remember that sigma is not a Hermitian matrix. So this basically means that this is not a sigma here was not a Hermitian matrix. So this basically means that this need not be a real number. Okay, so just as before, just as in this case, this equation we got the inverse Fourier transform for this matrix, and we got this equation over here. We can do the same thing in this case, and the equation kind of would look similar. So here the equation would look like IH bar del G del T minus epsilon minus plus sigma GT equals to delta T. Okay, so instead of this only E over here, we have this E plus sigma, because we have this E plus sigma over here. And earlier we used to have this, in addition to this, we used to have this infinitesimally small imaginary part I0 plus. But here I have not written this I0 plus over here, because this sigma already contains an imaginary part. So we did not write this here. Okay. Okay. So if we solve this equation, again the solution that we are going to get is kind of similar like the previous case. So GT would become minus I by H bar theta T e to the power minus I epsilon plus sigma divided by h bar t. Now let me tell you that in general this sigma would also be a function of energy. Okay, but why sigma would be a function of energy? Because we already saw that this sigma is basically tau gr, tau dagger, and gr is basically, gr was the Green's function for the reservoir, which is a function of energy, so this makes sigma to be a function of energy. Okay, but here in this case, to understand the physical essence of this matrix or this function sigma, we would assume that sigma is a constant, but know this, that sigma is an energy dependent term, which kind of makes this equation complicated to solve if this sigma becomes a function of energy here. But for simplicity, we would basically assume that sigma is basically a number here, a constant number, and we will try to find out the effect of sigma. Okay, so now sigma has a real part and an imaginary part. So this part epsilon plus sigma, so this part basically now becomes epsilon plus sigma is equal to epsilon plus real part of sigma, which we call sigma r, plus the imaginary part of sigma, which we denote by I gamma by 2. So I gamma by 2 gamma is basically equal to sigma minus sigma dagger. In case it is a matrix, then sigma dagger would basically mean the conjugate transpose of the matrix sigma. Okay, so gamma is kind of, if sigma is a number, gamma is kind of twice the imaginary part of this number sigma. Okay, so this basically becomes equal to epsilon dash, where epsilon dash is equal to this total part epsilon dash plus I gamma by 2. So the solution basically becomes g of t equals to minus I by minus I divided by h bar theta t e to the power minus I sigma plus not sigma, this is epsilon dash plus I gamma by 2. Normally for realistic devices or real devices, this gamma would kind of be a negative number, or the imaginary part of sigma would be a negative number. So we just, to make it simple, we just write it as minus gamma over here, and we just put a minus sign over here. Okay, I will not go into the detail why this is generally, why the imaginary part of sigma is generally a negative number, but right now just know that it is generally a negative number, as we have seen in the toy model. If you go to the toy model, you will find that the imaginary part of sigma is kind of negative. Okay, so there are deeper reasons why it is so, but we'll not go into the detail, because our intention is to just discuss the non-equilibrium Green's function formulation. Okay, so I would basically put again a negative sign over here, and this would basically give us minus I by h bar theta t e to the power minus, there is a t over here, so e to the power minus I epsilon dash t, then e to the power minus gamma by 2 t. Okay, so if I take this mod of Green's function square, so we basically get it to be minus e to the power minus gamma t. Okay, so here we kind of see two things. One is the effect of real part of this number sigma. So the effect of the real part of this number sigma, which is sigma r here, is basically to modify the eigen energy of the channel. Okay, so this was the eigen energy of the channel earlier, but now I would not say that its function is to modify the eigen energy of the channel, but because when a channel is coupled to the contact, you cannot define the eigen energy of the channel only anymore, because now the entire system consists of the channel and the contact. But the effect of the real part of this matrix sigma is basically to modify the available energy state inside the channel. Okay, so now the available energy state inside the channel basically lies at this energy epsilon dash over here. Okay, this is analogous to the case where we discuss coupling between two channels or between two 1D potential wells. So if you remember, we discussed this problem that when two 1D potential wells are coupled with each other, then what will happen? The energy levels inside this 1D potential well would mix up. For example, when this 1D potential well was isolated, the K state would be given by K equal to pi by L, 2 pi by L, etc. And for this case also, K would be given by the available K states inside this 1D potential, isolated 1D potential well would be given by K dash equal to pi by L, pi by 2 pi by L, etc. Now when these two are completely coupled, when these two are mixed up, which is kind of the extreme case, and when these two are mixed up and this two becomes a 1D potential well itself, that is the barrier in the middle is basically removed. In that case, this energy states mix up and form new set of energy states, which we are given by pi by 2L, pi by L, etc. Okay, this we have discussed earlier, so I will not go into the detail, and this is the concept of coupling. So the eigenstates gets modified once you couple two devices or two channels or even two atoms. When you couple two atoms, you get a bonding and an anti-bonding level. So similarly, when you couple this channel to the contact, the eigen energy inside the channel itself gets modified, and you cannot define the eigen energy of the channel anymore, but the available state inside the channel lies at an energy epsilon dash, which is basically epsilon plus the real part of sigma. So the effect of the real part of the sigma is to modify the available state inside the channel. Okay, so this is equivalent to coupling between two structures. Okay, now this term, the imaginary part of this sigma, this basically defines the rate at which the wave function basically leaks out of the channel. That is why when we take the mod of the Green's function and square it, then we are supposed to get the temporal dynamics of the excited electron particles inside the channel. Okay, so remember that G denotes, so we are discussing about the channel now, so G basically denotes the response dynamics or the temporal response dynamics of the channel when it is excited. Okay, so mod of G square or a square of the modulus of G would basically denote the temporal response of the electron particles or the hole particles inside the channel once it is excited, and this is basically given by e to the power minus gamma t. So this imaginary part, which is gamma, basically denotes how fast the excited electrons inside the channel decays with time. So remember that excited electrons in this case would mean anything which causes current flow, because current flow is caused by an excitation. So whenever electrons are entering inside the channel, those are basically excited electrons, or whenever holes are entering inside the channel from an outside contact, they are basically excited holes. Okay, so in this aspect, excited electrons basically mean the electrons which are causing current flow in a very layman's terms. Okay, in very layman's terms, it would mean the electrons which are causing current flow. Okay, so it basically, this imaginary part denotes how fast this excitation is decaying from the channel. Okay, so that is the physical essence of this function sigma. Now let us come to another important aspect of the Green's function, and first I would like to remind you of two things. One is the local density of states, which gives the density of states at energy E, density of states per unit volume at energy E at a local point. Okay, and second is that what we stated earlier, that the relation between two operators, I am not writing it, but I am just stating it because it's time consuming. So the thing is that the relation between two operators does not change when we move from one basis set to another, and any equation between operators, or any equation which relates operators, also does not change when we move from one basis set to another. So the relation between two or more operators, or any equation connecting two or more operators, remain unchanged irrespective of which basis set we use. So this we have shown earlier with the help of a few examples. So let me define the concept of spectral function. A E, which is equal to the Green's function E minus the conjugate transpose of the Green's function GE. And if we are using a basis set in space, or if we are using a spatial basis set, then the trace of AE, trace means basically the sum of the diagonal elements, this gives us the density of states, and the diagonal elements of the spectral function, that is AMME, if we are using a spatial basis, then AMME gives us the local density of states at point M and at energy E. So of course, when we define this term as the local density of states at point E and at point M and at energy, it becomes evident that the total density of states is basically the sum over all the points in space. So the sum of the diagonal elements, so AMM is basically a diagonal elements of this spectral function A. So the sum of all the diagonal elements basically gives us the total density of states within the channel. Okay. Okay, so it's very complicated to prove the rigorous equation, and we'll not go into the rigorous mathematics to prove this equation, but what we will do is we will take some examples to understand this case. Okay, so let us just take the case of an isolated channel or an isolated contact, let us say, whatever, but it is isolated, so its eigenenergies are well defined. And in case of isolated contact or channel, the Green's function, let us define the Hamiltonian first. The Hamiltonian is basically, if we are taking the eigenspace basis or eigenvector basis, then the Hamiltonian is defined by the eigenenergy in the diagonal terms. So in this case, the basis is basically the set of eigenvectors or the set of eigenfunctions of the Hamiltonian. Now we define another function, we define another matrix which has delta functions at the energies corresponding to eigenenergies. So delta E minus epsilon 1. So we have the delta functions at the energies corresponding to the eigen energies of the Hamiltonian, and all other elements are 0. And in mathematical language, this matrix is known as delta E I minus H. Okay, minus H basically comes from this minus of this eigen energies of the system, and the delta function over here is basically reflected in this, on these functions here. Okay, so if we take the trace of this matrix now, so trace of delta Ei minus H is equal to summation over n delta E minus epsilon n, and of course this is the density of states of the system, and there is no doubt about this fact. Now if we can show that this matrix G E minus G dagger E equals to delta Ei minus H, then we can say that the trace of this matrix equal to basically gives us the density of states. Okay, so let us now see what we get. So we have already seen that the Green's function G of E is basically given by a matrix of this form. So if we take G minus G dagger, of course all the elements in G dagger would be subtracted from G. So let us take one particular example. Let us take the first row first element G11 E minus G dagger minus G dagger. Let me write in a different way here. I'll put brackets to denote matrices, otherwise the notation becomes difficult. So GE 11 minus G dagger E 11. So what is the first row first column element of GE? So this is E minus epsilon 1 plus I delta. And what is the first row first column element of G dagger E? So G dagger is basically the complex conjugate transpose of the matrix G. So this imaginary part becomes negative here, so this basically becomes minus I delta. Okay, so this basically now becomes plus delta square and on the top it becomes 2I delta. So we actually have a minus sign over here, and I argue that in the limit delta tends to 0, so in the limit that delta tends to 0, 2 pi delta E minus epsilon 1 is given by 2 delta divided by square here, so divided by E minus epsilon 1 square plus delta square. So how to understand this? So remember that a delta function has two properties. It is 0 at all points except at epsilon 1 equal to 0. So if epsilon 1 is not equal to 0, in that case this becomes finite and positive, but delta is actually infinitesimally small. So at all points except e not equal to epsilon 1, this function is basically 0. Okay, and at e equal to e1 or e approximately equal to e1, this function is basically infinite. So let us check. If e is equal to e1, if e is equal to e1, then this term becomes 0. So if this becomes 0, this function basically becomes 2 divided by delta. Okay, so 2 divided by delta is infinite, so this function is infinite at e equal to e1. And the third property is that the integral of delta e minus epsilon 1 from minus infinity to plus infinity must be equal to 1. Okay, so let us check out if this property also holds. So 1 by 2 pi integral from minus infinity to plus infinity to delta divided by e minus epsilon 1 square plus delta square. So what does and then dE. So what does this give us? So this 2 comes out of this picture, so 2 delta divided by 2 pi over here, and then minus infinity to plus infinity 1 dE divided by e minus epsilon 1 square plus delta square, and this is equal to delta divided by pi tan inverse 1 by delta tan inverse e minus epsilon 1 divided by delta, and within limits of plus infinity and minus infinity. So now when e is equal to plus infinity, then this tan inverse basically becomes equal to pi by 2. So this becomes delta by pi 1 by delta, then pi by 2, and when e is equal to minus infinity, then the entire argument becomes minus infinity. So this is equal to minus pi by 2. So minus of minus pi by 2 here. So we basically get delta by pi into pi by delta, which is basically equal to 1. Okay, so it is proved that 1 divided by 2 pi times this function is equal to the delta function. So this entire thing must be equal to this 2 pi times this delta function here. Okay, so this 2 pi delta e minus epsilon 1, this is equal to limit delta tends to 0 to delta divided by e minus epsilon 1 square plus delta square, and the second relation which we have is g e 1 1 minus g dagger e 1 1 is equal to minus 2I delta divided by E minus epsilon 1 square plus delta square, which is equal to minus I 2 pi delta E minus epsilon 1. Okay. Now remember that our density of states is basically given by the density of states is equal to summation over n delta E minus epsilon n, and this is equal, from this relation over here, this is equal to the trace of G E minus G dagger E multiplied by I divided by 2 pi. Sorry, we have a I over here, so I just forgot to write it. So we have a I over here, and we have a 2 pi over here, and we also have a 1 by 2 pi over here. Okay, so this is basically equal to trace AE divided by 2 pi. Now this spectral function AE equal to I GE minus G dagger E. This, although we have showed that this is the spectral function, and 1 by 2 pi trace of AE basically gives us the density of states, and in this basis set, where in the eigenspace basis set 1 by 2 pi AN in E, this basically gives us the density of states at energy E, the density of states at energy E for the eigen state n. Okay, because we have used the eigen space basis here. Now if we would use the real space basis, what would this AN, so this is for the eigenspace basis. If we would use the real space basis, remember, as I told, that the relation between different operators or an equation which relates two or more operators basically remains same irrespective of which basis set we use. So even if we use space basis set, all these things are going to remain the same. Now what would this element 1 by 2 pi A n n E mean in case we use a real space basis set? So in this case, this element would basically mean the density of state at energy E at the point n, which is basically the local density of states at point n. Okay, so if you use real space basis, this each of these diagonal elements of the spectral function basically give us the local density of states. Okay, Similarly, we can like the spectral function, we can also define the density matrix. So the density matrix rho in the eigenspace basis or in any other basis, it can be defined in the same way, but we are using the eigenspace basis now because it is easier to understand. So this is basically given by the Fermi function at the different eigenstates. So this is f0 epsilon minus mu, epsilon 1 minus mu, and the diagonal elements that give the occupancy of the different eigenstates. Okay, so f0 epsilon 2 minus mu, the diagonal elements are non-zero and all other elements are 0, and this matrix would kind of look like this. And if we take the trace of rho, we are going to get the total electron density n. So the total electron density n is the trace of this matrix rho. Okay, now rho can be defined in terms of the Hamiltonian in another way. So this matrix rho can also be written as the Fermi function of the Hamiltonian itself. So f0 h minus mu I, and then since this equation is valid in the eigenspace basis of the Hamiltonian, this equation is also valid in any other representation of the Hamiltonian, or this equation is valid irrespective of which basis set we use to represent the Hamiltonian and other operators. Okay, so there is another way of writing the matrix in the again in the eigenspace basis, which is minus infinity to plus infinity dE f E minus mu delta EI. So I is again a matrix minus H, which is kind of a representation of the spectral function in the eigenbasis. So we can replace it by the spectral function. So integral of minus infinity to plus infinity dE f E minus mu the spectral function AE, and here we have dE divided by 2 pi. So since these equations are valid in the eigenspace representation of the eigenspace representation of the Hamiltonian, these representations are equally valid, or these equations are equally valid in any other representation or any other basis set as well. Okay, so till now we have discussed things for an isolated channel mainly because we kind of wrote the eigenstates, we wrote the Hamiltonian directly in terms of the eigenspace basis of the channel or any device. Now let us see what is the effect of sigma on the density of states of a channel. Okay, to make things simple, we will again assume that the channel consists of only one state or one point or one basis function. It might be an energy basis function or it might be a space basis function, but it can only be represented by only one basis function. Okay, in that case, so this Green's function GE, that if you forget, this was basically EI minus H minus sigma inverse. Now when the channel consists of only one basis function, or the channel can be explained by only one basis function, in that case this Hamiltonian is given by the eigenenergy of the basis function, and this number sigma, this matrix sigma basically becomes a number. Okay, so channel with one basis function, so in this case GE becomes a normal function, it is no longer a matrix, and this basically becomes a number E minus epsilon, where epsilon is the eigenenergy of the basis function, minus sigma is again a number inverse, which is equal to E minus E dash plus I gamma by 2. Okay, so let me remind you that E dash was equal to epsilon plus the real part of sigma plus the real part of sigma, which was equal to epsilon plus sigma r for real, and minus gamma is equal to sigma minus sigma dagger. So this is basically the imaginary part of sigma divided by 2. So half of the imaginary part of sigma. Okay. So let us just see what is the spectral function in this case. So the Green's function is basically given by GE equals to 1 by E minus epsilon dash plus I gamma by 2, and the spectral function AE is equal to I times GE minus G dagger E. Since G is now a function, G dagger E basically becomes the complex conjugate of that. Okay, so I 1 by E minus epsilon dash plus I gamma by 2 minus 1 by E minus epsilon dash minus I gamma by 2, and this now basically becomes I E minus epsilon dash square plus gamma square by 4, and here on the numerator we basically have minus I gamma, and this I and this minus I, this makes minus I square, which is equal to 1. So the entire thing is equal to gamma divided by E minus epsilon dash square plus gamma square by 4. So the density of states is just given by the spectral function divided by 2 pi. It's actually the trace of the spectral function, but since spectral function is just consists of one element here, it's not a matrix, so this is just a spectral function divided by 2 pi, which gives me 1 by 2 pi gamma divided by E minus epsilon dash square plus gamma square by 4. So earlier when it was not coupled to the channel, then this sigma element was not there, and there thus the density of state would be given by, so for isolated channel, so this is for basically channel coupled to contact. Okay, for isolated channel, this sigma is equal to 0, and we add a very small term which is I eta. So for isolated channel, the density of state, remember that it was basically equal to 1 by 2 pi limit delta tends to 0 delta divided by E minus epsilon square plus delta square. So I think it was 2 delta over here. Okay, so this was for isolated channel. and note that this was equal to a delta function, but note that here due to the presence of this number sigma, because sigma is not 0, due to that this we have this finite value of gamma over here. So this entire thing is not a delta function, and depending on what is the value of gamma, this function would basically look more broader. Okay, this is known as a Lorentzian function, and if we plot this function with energy, let me show you what we get. We have this density of states as gamma divided by E minus epsilon dash square plus gamma square by 4 and 2 pi over here, so 2 pi. So this function looks this function is centered around epsilon dash. As you can see that if you reduce this energy E slightly beyond epsilon dash, you would get the same value as if as you would get if you increase the value of E beyond epsilon dash by the same amount. So this function is symmetrical about around epsilon dash. Okay, so this is known as a Lorentzian separate function, and this function exactly looks somewhat like this. Okay, and if you integrate this function, you would again get a value of 1. Okay, if you integrate this function over energy, you would get a value of 1. Now if you reduce gamma, or let us say if you increase gamma, what would the function look like? So if you increase gamma, this function is going to look somewhat like this. Let me just rub it here. Okay, and if you reduce gamma, this function is going to look sharper. So this is for, let us say this is for gamma 3, and this red one is for let us say gamma 2, and let me draw another plot with gamma 1. So if we reduce this gamma, we would get a sharper plot, but which is distributed over a less energy. So we get some plot like this. It's difficult to draw it here. So yeah, so gamma 1 is basically less than gamma 2, it is basically less than gamma 3. Okay, and the integral, irrespective of what is the value of gamma, the integral of this density of states over energy is basically 1. So what does this sigma matrix do, or this function sigma do to the density of states? So it basically broadens the density of states. Okay, once you couple your channel to the contact, the eigenstate of the isolated channel no longer remain the eigenstate of the coupled channel. Okay, and here the eigenstate is broadened, and you get a broadened density of states. Okay, now this basically brings us to another function or another operator, which is known as the broadening matrix. So the broadening matrix is basically given by capital gamma E, which is basically given by I sigma minus sigma dagger. Okay, and if when this was the channel was, or the channel could be explained by one basis function, in that case this capital gamma reduces to a number which we took to be gamma. Okay, minus gamma to be precise. Okay, only gamma. Okay, okay, And there is actually a very beautiful essence to uh, this broadening of density of states. It contains more of a physical sense from the energy time uncertainty principle. So remember that we had this energy time uncertainty principle, which denotes that delta E delta T is greater than equal to h cut by 2. Now, as we saw that in case of the isolated channel, we had a very sharp energy level, and this is also the case of different atoms. Like when we have atoms, isolated atoms, they have orbitals which have very sharp and well defined energy levels. Okay, so here also, when the channel could be explained by a single basis function, the isolated channel, it had a very sharp and well defined eigen energy. And in case of the isolated channel, the electron could not actually go out of the channel because it's isolated. So in that case, the electron or the wave function exists inside the channel for infinite duration of time. And so this if this delta t is infinite, this delta E is basically 0, and so the electron can exist at a very sharp energy level. The energy levels are well defined and sharp. On the other hand, if the electron basically leaks out of the channel via the contact to channel coupling, in that case delta T becomes smaller and larger is the value of gamma. This delta T becomes smaller because electron basically gets out of the channel very fast. Okay, if gamma is larger, in that case the decay in the wave function is the rate of decay of the wave function is higher. This we saw earlier. So the electron basically exits from the channel very fast, and so the uncertainty in time delta T is basically lower, and this basically increases delta E. So what was a sharp energy level before has now broadened in energy, and it has become basically Lorentzian shaped density of state. Okay, the earlier the density of states was like a delta function. Now because the electron can leak from the contact, electron can leak from the channel into the contact, or electron can enter from the contact into the channel, this delta T has reduced, and larger is this value of gamma, delta T is smaller, and so since delta T is smaller, delta E must grow larger to basically preserve this uncertainty relation here. And so what was a very sharp eigen energy state before has now broadened in energy. Okay, and larger is the value of gamma, smaller is delta T, and so this delta E is supposed to grow larger. Okay, so let us do up to here today, and we will be needing all these concepts when we actually go to the transport model, and when we actually go to the equations for transport in the non-equilibrium Green's function formulation. So these concepts are basically important. So take your time and let this concept sink in, and you also need to think about it a little bit. So let us do up to here today. Thank you everyone.